Adam, the co-founder and CTO of SkyMind. So we're a little of an outlier for this conference. We're actually focused on AI. I usually predominantly speak at big data conferences. So this is a little new for me. So if I go too fast on any of these concepts, I'm more than glad to take questions or point you at introductory resources. One thing I can't link to right now, but I'll just mention here, I'm the co-author of an O'Reilly book called Deep Learning, A Practitioner's Approach, which actually targets Java developers in doing deep learning. So I created the package Deep Learning 4J, Deep Learning for the JVM, and the book is based on that. So you don't need to know big data. You don't need to know Hadoop and Spark. If you just want to jump in, we have introductory content for people like you. And so that's why we called the book Deep Learning a Practitioner's Approach. So basically, you're an AI, maybe you're an ML practitioner and you're building applications, and you just, you want to jump into this and you need to know where to start. That's who the book is for. So if you want any links to any of that or whatever, let me know after the talk. And so what we're going to cover today is GPUs in production. So GPUs are basically an alternative kind of chip that you use for running numerical calculations. So I'll cover that throughout the talk. So starting off, this is SkyMind. I live in Japan. Our team is distributed globally around the world. We're 20 people. We co-founded in San Francisco in 2014. I started Deep Learning 4J in San Francisco in 2013, and I moved abroad. Turns out Asia loves us. So most of our traffic actually comes from China. So because we have documentation translated to Mandarin, Korean, and Japanese, and it turns out that paid off. So I focus a lot on our Asian market and running our engineering team that's distributed around Asia. So that's SkyMind. So what I'm going to do first is I'm going to define production. So production is something a lot of people just they don't really think about it too much because, they just think, oh, well, production is whatever we deploy to. Well, it turns out there's various kinds of deployment depending on the company size. So there's startup production, right? So startup production is where you have cloud. You're probably on AWS. You're probably not, you might be, if you're using any sort of big data stack, you're probably using Elastic MapReduce. You're not thinking about microservices. You're not thinking about, you might be thinking about Kubernetes or some of these newer fangled container things, right? But at the end of the day, you have very basic scaling problems. A startup doesn't have a lot of data. That being said, the startups that actually do some sort of deep learning usually are doing it in very small data sets, and they blog about it, and they say, look how awesome we are. But what they don't tell you is they don't have many users, they don't have a lot of data, and chances are they're usually chances are even the way they deploy to production is kind of weird. And so what you'll find then is you have this Java conference, you have like Pivotal, Lightbend, and all these other guys here, and they're talking about all these large-scale enterprise problems. That's who we target as well. So I'm hoping most of you guys are kind of in the second space, which is enterprise production. That's when you're focusing on microservices, the big data stack, continuous deployment with Jenkins, and things involving that. Probably having a Hadoop cluster. A lot of you probably use, I'm just going to assume you guys use Spring, because I saw the room filled with, I know for the Spring talks, I see everybody in the room. So that's probably what most of you use in production. So what I want to do is kind of show you deep learning in the context of how do I use it from a Spring or even just a play application, right? And so I'm not going to go into math. There's no linear algebra in this talk. This is actually an infrastructure-oriented talk. So enterprise production will be the predominant focus. But what I want to just kind of allude to is this idea of research production. So there's not a big, so this is Python land. So there's a huge emphasis on a stack called MPI. which is kind of it's basically for GPU to GPU coordination, and it's how distributed systems were done in the 80s. If you want, look up the field HPC, high performance computing. This is how physics labs are run. All distributed systems code happens in C++. And this is what the MATLAB and Python people interact with usually. So it's actually a very different stack from what you probably run at your company. So research production is actually a very different set of tools. So now you'll kind of see why I wanted to kind of define production for you, because you'll probably just see we run deep learning in production and no one defines what it means. I hope this kind of alludes to a wide variety of different implementations and different ways of doing deep learning in production. And even in the context, actually, I should mention this also. Even in the context of GPUs, right? Like it turns out, GPUs are not commonly deployed in large big data clusters. They can be, and that's what I'm going to show you. That's what I'm going to show you how to do today. Okay, so one other thing I want to mention is research. So you have various kinds of research clusters. So there's no production deployment happening here. There's no focus on good software engineering practices where 100 developers can work on the same product. So they don't need Java. They don't need static typing. They don't need a lot of the best practices. They just need something flexible and quick that allows them to express mathematical expressions. And so that's when you're typically going to use Python and NumPy. Sometimes you might use C code, like if you have, sometimes people are doing a lot of GPU systems research, and it turns out those folks usually use C. So there's a dialect of C called CUDA C that you usually use for programming GPUs. And so there's tons of libraries, including ours, that wrap these things. So you guys don't need to touch C in order to use a GPU. But when you're doing research, if you need to write a faster convolution algorithm, you're probably going to end up having to do some C code. And so that's what you're typically using from a higher level library. But sometimes folks will use C when they're writing new neural networks. So then there's kind of the applications research. Maybe you're like a mid-scale startup, like say Pinterest, Airbnb, and you're doing some sort of research and development. And so you're probably going to be using AWS, and you might be a consumer of just say their new GPU nodes. So if you're using those, then you're spinning up resources and you're shutting them down. And so that's typically happening in the cloud. And then actually I just realized that this slide should have said on-prem research. Or sorry, yeah, so on-prem, anyways. So just know that there's another kind of cluster where you're typically doing other kinds of production, which is like HPC, video transcoding. So it turns out if you're like Daily Motion, you actually use GPUs to render and stream video. And so that's just an alternative application that you might not be thinking of. This is also something that Netflix does. So a lot of companies, if they're doing video streaming infrastructure, you use GPUs to serve everything. The reason for this is because GPUs are really good at processing images. They're good at shrinking and resizing them and things like that on the fly. And so you're going to be rendering things from the GPU. And then finally, what we're going to mainly talk about today is big data hybrid clusters. So this is where you're talking about resource schedulers, Mesos and Yarn. So if you haven't seen a resource scheduler before, think of you having 10 nodes. So 10 virtual machines, virtual private servers, whatever terminology you may be used to, 10 containers. You just have a cluster of 10 nodes. And you just want to view that set of nodes as a pool of resources. Like so you want to run a distributed job on 10 nodes. Well, how do you do that? And how do you do that? How do you do that easily? You use a scheduler. So what you do is you say, I want to run this distributed job on 3 GPUs and 8 CPUs using 256 gigs of RAM. And then what you do is you schedule your job you put your job on the scheduler. And it says, okay, given my current pool of resources, do I have anything available? When it does, it'll put the job, it'll basically run the job and distribute it across your cluster. And so that actually is what's going on underneath when you use Hadoop or Spark, and you're running some sort of a MapReduce job or a count or anything like that. What's actually going on is Hadoop and Spark are actually just a client for a distributed scheduler. And so that distributed scheduler is what you use when you want to run large scale, like petabyte level data processing. And so that's what we're going to see a little more in depth here. So when we're doing distributed deep learning, we're usually using a scheduler. And finally, of note, when you hear about GPUs being used in production, one of the coolest applications of this is actually self-driving cars. So NVIDIA actually does. So NVIDIA is the dominant GPU chip maker. You know, so they have literally 90% of the market. AMD sort of competes with them, but there's just no comparison. So NVIDIA basically monopolizes the German car makers. So they have, I believe, most, if not all, of the German car makers as customers doing object recognition for things like stopping your car, detecting obstacles, and eventually doing self-driving cars. So this is actually happening actively today. So people are driving on roads using GPUs. And finally, the one we all wish we had, Google and Facebook scale clusters. We have unlimited resources and an unlimited budget, and good engineers teaching us how to do everything. You don't have the scale, and I don't either. So we all use Java. Here we are today. All right. So this is what I call a big data hybrid cluster. So you have your standard JVM stack. You have Hadoop. You have, and when I say Hadoop, I actually mean a combination of HDFS and probably Zookeeper. I think those are the only components of the Hadoop ecosystem people mostly use nowadays. So when you think of Hadoop, you're usually thinking of distributed storage in combination with distributed node communication, which in this case is going to be Zookeeper. So Zookeeper is used for consensus. Hadoop file system is used for basically storage, right? Like, so what you do is you have Hadoop daemons on each node, and it knows how to use the local disk. And then what HDFS does is it allows you to view a whole, like a petabyte of data as just one single unified file system across however many nodes you want with built-in fault tolerance. And then you have tools like Flink and Spark and Storm that know how to access HDFS and run distributed compute across your distributed file system. And so that's kind of where your large-scale business intelligence applications happen. So you're running Hadoop as a service, you're running MapReduce as a service, and you're running it across however many nodes you need. And then underneath that is Mesos or Yarn. So what I'm showing here is Mesos. Mesos is kind of in the lead for GPU provisioning. So with Mesos, you can actually use GPUs as a resource. So if you have a Mesos agent on each node, it will actually auto-discover, if you have the CUDA drivers installed properly, it will actually auto-discover where the GPUs are and allow you to schedule it as a resource. And then Spark will then be able to use GPUs as part of the job. And so this is active now. So Spark 2.0 supports GPUs now with Mesos. And so that's actually a lot of how we leverage and train distributed deep learning on Spark. Is we typically use Mesos for that. So what happens is you define a Spark job. You create your Uber jar. So I'm assuming you guys know Maven. So with Maven, you use the Maven Shade plugin. You create an Uber jar, and you create a main class. And that main class is what controls what Spark does. You then send that jar via Spark submit to your cluster, and you say, I want to use 8 GPUs and 256 gigs of RAM. Spark then knows how to talk to Mesos and run the compute on the allocated resources from Mesos. And so this is basically how you do training, right? So when you're in production, there's two kinds of usage modes of GPUs. There's training, which is building a model. So that's when you're building your model. That's when you're training your model. That's when you're doing neural net training. And then there's inference. So inference is actually where things get interesting for you guys, because this is probably where a Spring or Play or web developer is going to touch, that's where you're going to touch machine intelligence. This is probably what 99% of you are going to interact with. Somebody else typically trains everything on your cluster. I'm aware that big data is kind of an alternative set of, even though it's the same programming language, it's probably a different set of skills than maybe you guys are used to. And so one thing I want you guys to realize is you guys will probably be interacting with a model, using a model, like consuming a model as a POJO, a plain old Java object. So you're going to embed it, so you're going to declare it in your Spring configuration, right? So you're going to put an @bean, you're going to instantiate the model, and then you're going to use the model as an API. And so we call that inference. And so when you deploy a model, what you're going to do then is you're actually going to deploy microservices. And those microservices are basically going to take in requests via REST and return results. Like this is a dog, this is a cat. The housing price is going to be $32,000. Whatever decision you're trying to get it to make. And so when you're thinking about GPUs, you can also use GPUs for inference here. So NVIDIA actually has a neat little piece of technology called TensorRT. So TensorRT is basically a way of running compute on GPUs. It's without the overhead of sending data back and forth between the CPU and the GPU. And so why do you need this special piece of technology? It's because the GPU itself is actually a separate server. It's actually a separate server. It has its own memory space, and it's meant for a specialized set of applications. It's actually not a general, it's kind of a general purpose computer, but in reality, it's only meant for certain kinds of applications. So GPUs are specialized for matrix computations. And this is actually why you need a special programming language to run anything on the GPU. So anyways, what happens is you send data from your local CPU RAM to the GPU via PCIe bus. And so you have all these extra connectors on the GPU itself that's connecting your CPU to your GPU. And when you're sending data back and forth, that obviously incurs some overhead. So what you have to do if you want to take advantage of the GPU, not to mention all this other stuff, but when you want to take advantage of the GPU, you actually have to know something called how to do latency hiding, which means sending data to the GPU in the background while running compute in parallel. So what you do is what you're doing is you asynchronously, so asynchronous, there's that keyword again, you reactively send data to the GPU in the background, and you want to run compute at the same time. And the goal is to always have ETL, extract, transform, load, loading the data into the GPU, and having compute run in parallel. That's how you get the throughput of the GPU where it has thousands of cores, but this bandwidth, this overhead of data transfer. So again, that's called latency hiding. So these frameworks take care of that for you, including what we do. So when you're doing deep learning, you have a pipeline where you're running data, you're running compute from disk, you're loading data into memory, you're loading data into a matrix, you're sending it to the GPU and running all your computations, and you're getting some sort of result out. And then, so what we do, when we do training, we actually typically use something called parallel wrapper. Parallel wrapper is a piece of software that allows me to use every single core and every single GPU on my box, on my node. And what we do in parallel wrapper is we actually handle asynchronously loading the data and running the neural network in parallel using all your cores. And so what we do is we load data in the background, we send it to the GPU, and we just keep everything running. So one thing we can do is we can specify something called a prefetch buffer that will say, given this much RAM, I'm going to preload these many things into the GPU memory before my compute actually runs. And when you do that, you can actually get the throughput. And so this is actually what we do on Spark. It's the exact same idea. So when you run a MapReduce job, or when you're running map and reduce, or even, okay, so think about Flux. So Flux is a Spring thing. Lagom and Scala also have this functional paradigm of fold, reduce, map. When you're running all those computations, That's basically what you're doing on Spark. So what we do is we run map, and when we run a map operation, we're asynchronously loading all that data into memory and running all the training like that. So we break up our data set into partitions. We run map, and map loads a neural net, loads some data, runs an update. Like when you're doing you're doing your gradient descent, which I'll show you in a bit. I actually have a live demo for you. Anyways, just say for now that your neural net has an error and it learns. And when it learns, what happens is you're pairing basically a data partition with a set of weights, and you're running a matrix multiply operation. And that matrix multiply operation runs on the GPU. And so when you're doing training, or even when you're doing neural networks at all, you're loading data from RAM, you're running it through the GPU, and you're getting a result out, and then you're using that result in your application. And so that's what happens. That's what happens all the time. Is when you're thinking about latency or training time, you have a combination of ETL and a combination of RAM and all sorts of crazy hardware configurations that you need to think about when you're doing all this training. So the core of it is the core of any deep learning time that you're doing is going to be doing is a summation of the training time, or you decompose the training time down to ETL time and matrix compute time. And so Mesos and all this, Mesos and Spark and all that allows you to do this on an arbitrary scale. So that's the whole point of using the software, is you can say, I want to use 1,000 GPUs for this job and train a big neural net. And so why do you need to do this? So a big reason for this is if you have a GPU up for a week, you're spending $30K on Amazon. This is actually to save money. So for example, why would you need to wait a week? That's because that's how long it takes to train ImageNet. On a single node, you have over 1 million examples, 1 million images. To train a neural net from scratch and get good results on, in this case, more than 1,000 classes of objects, various kinds of animal species, fruit, you name it, right? Large data set. That takes more than a week on a single node. And so when you're renting a GPU, that gets expensive very quickly. This is why people tend to take pre-trained models and use them instead of trying to train their own. Because not only is it difficult to train a model, but it can also get expensive very quickly. And this is also why you need a specialized chip for actually running the compute, running these neural net operations and doing this training. So this is how we do it in Deep Learning 4J. So this is kind of an overview of the ecosystem itself. So on the left there, you see raw data, and then you see basically what we call our distribution, our set of software for running and deploying neural networks. So we have Deep Learning 4J, but Deep Learning 4J itself is actually a set of libraries for building deep learning applications. We have an ETL library, extract, transform, load library called DataVec. That's when you're pre-processing data. That's when you're cleaning up your data, normalizing it, and turning it into vectors. This is a process called vectorization. ND4J, I actually ported NumPy to Java. So NumPy is a de facto matrix package. It looks kind of like MATLAB. If you've ever used MATLAB in school or something, it looks kind of like MATLAB. They have this concept of an ND array, and it turns out you use ND arrays when you're doing when you're building neural networks. You're basically using a math library, a matrix library. But why do you need an ND array? Neural nets themselves can actually be made up of something called a tensor. You can actually have greater than 2 dimensions on a matrix. When you have a greater than 2-dimensional matrix, you have something called a tensor. And so when you have tensors are by default computationally expensive. So I'm not going to get too much into the rabbit hole there. If you have any questions about tensors, I can talk about that later. But keeping going, we also have something called arbiter. Arbiter is for basically automatically tuning neural networks. So you define a hyperparameter space to search. You run the hyperparameter space, and you say this is the best configuration. So you can actually automatically generate a configuration. So again, this is what I want to say. This is a set of software for building deep learning applications. We also have things supporting deploying deep learning as microservices. So you can run everything as a play application or a Spring application, and you can expose your model as a REST API. So when you if you haven't deployed a machine learning model before, think about every time you hit Amazon or do a Google search and you hit submit, you're sending a REST call to some sort of an AI model. That AI model is running some sort of a matrix computation and giving back the likelihood that you like cats, or the likelihood that you want a certain web page. So every time you're using some sort of a web page, you're probably using an AI-based microservice. So an example of this is Amazon Research is a big user of deep learning 4J. So they actually use us for a lot of their product recommendations. So they're predicting consumer demand. And so when they do that, they're using Java, they're deploying Java-based microservices, and they're figuring out what you want to buy. And that's and components of that are using deep learning 4J. So just as an example of, if you're a Java-based machine learning shop, which there's a lot out there, my software is probably powering some of your clicks. And this all happens as microservices written for the JVM. And then finally, aside from that, is integrations with various kinds of pieces of the JVM ecosystem, such as Flink and Spark and Kafka. So we actually have a library called DL4J Streaming, and DL4J Streaming allows you to connect to Kafka and use Kafka to basically serve data to your neural network. So that's all in here. I could spend all day on this. I'm only going to mention one more. So I'm only going to mention one more thing, which is at the bottom, where you have CPUs and GPUs. So I also implemented some. I also write C code. It turns out, I also write CUDA C code, and so I wrote something called libND4J, which basically automatically connects to hardware accelerated libraries such as Intel MKL and NVIDIA's cuDNN. So we connect to hardware accelerated libraries, and you can then use those from Java. You never see this. We wrote all of it for you. And so here's an example of our training UI. So in this case, I don't know if you guys know the MNIST data set at all, but the MNIST data set is basically 60,000 handwritten characters written from 0 to 9. And this is a neural net called the LeNet architecture, the LeCun net. So Jan LeCun invented this neural network. He's the head of Facebook research. So he invented this a long time ago. Anyways, so this is his convolutional net architecture. This is a configuration, and this is a data scientist actually monitoring error going down over time. And so if you're curious, this is actually a play-based web application. So everything I'm mentioning here is Apache licensed, by the way. So you can use this for whatever kinds of applications you want. Okay, and then this is an example inference pipeline. So in this case, we have the web application at the top. This is your REST API exposing your model. You have in the middle, you kind of have your trained model. That trained model is connecting to a CPU and a GPU, and that CPU and GPU is running computations that allow the neural net to make decisions. And then you're connecting to a data source such as logs or IoT, and then data is being sent in to Kafka. You run a vectorization pipeline. So a vectorization pipeline is data vec. This is where you're running like an extract, transform, load job. This is where you're cleaning up the raw data, normalizing it in a way a neural net can understand, and then you're returning a result and then serving that to your web application. So one of the things I want to be clear about here is, ML and machine learning, like the math, is actually fairly learnable. It takes about high school math to understand the basics of how to do this. So a great guy I want to call out in the front row is James Weaver, who actually learned, works at Pivotal. Talked to him about deep learning 4J, who actually learned machine learning from scratch using just our content, actually. And so he learned just enough, and he actually presented some very impressive applications of neural networks just using Spring Boot. So it turns out this stuff is learnable. So talk to him about how he did it. I'm a library author, so I have no clue what you guys do. Just that being said, I'm happy to link you to resources though. So that application I just mentioned is going to look something like this. So if you know how to do software engineering, that's actually, and systems, that's actually harder to do than the math part. You can actually build a fairly basic application pretty quickly. Deployment in infrastructure is actually the hard part. You guys actually know how to do this better than the people who do deep learning research. So I hope feel good about yourselves, because that's actually, Java and static typing is actually a big problem for these people. The number one cause of support on we have a Gitter channel, has over 4,000 people in it. Gitter is a live chat. The number one question I get is, what's Maven? You guys know what Maven is, right? So here's the thing, like most people don't even know, the people who know the math don't know build systems. So I welcome anyone who knows Maven into my channel, because I want more math questions. Please. All right. So, so some things to think about when you're running jobs on a GPU cluster. Memory management. So GPUs themselves don't have very much RAM. They have on average 12 to 24 gigs of RAM. That's it. So when you're running computationally intensive jobs, you can't load very much into memory at once. This is why I'm saying you need multiple GPUs, because what you're going to do is you're going to take your terabyte of data or whatever you have on your cluster, and you're going to shard the problem into multiple GPUs. And then you're going to run as many of your partitions of your data in parallel as possible. And you're going to maximize whatever RAM you have in your GPU. Throughput. So throughput includes the overall training pipeline itself. Oh, what time do I go to, by the way? 5? Okay. So so you know what? I'm gonna take questions later. This went longer than I thought it did. So I'm gonna point out one thing. Again, we do all this for you. You guys kind of know how Java works and all that. Just of note, we wrote our own GPU garbage collector. So you guys don't even have to know how GPU memory management works. We actually handle it. We actually think about these things for you. Okay, got it. Okay, cool. Okay, well then I'll just keep going then. Okay, so I'll try to reserve like at least 15 minutes for questions. So the only other thing I'll mention is from CUDA, from Java, you can actually manage your GPU. And so what we allow you to do is we actually allow you to configure things like, do you want deep learning to use all your GPUs? How much memory do you want it to use? It turns out GPUs also have a neat L1 cache, and you can configure how much of that cache to use. And so one unique thing we did was we actually implemented memory management for cuDNN, NVIDIA's library, and our own matrix libraries. And so that's special. You normally you usually have to know how to compile CUDA-C, or you normally have to do your own memory management with other libraries. With us, you don't have to. And so this being controllable from Java is novel, because all of a sudden this allows web developers to treat a CUDA environment as another POJO, as another thing you inject via dependency injection. So there's some neat things you can do with this. You could expose this as, say, a REST API and implement and actually instrument your GPUs like this. So you can actually capture whatever the environment is, and then expose all your GPUs and chips as just a simple piece of JSON for you to use monitoring software on. So this actually allows you to do some neat applications. It's just something to keep in mind. We do all this via something called Java CPP. Java CPP does memory management for Java. We actually do all of our own memory management off heap. So we don't use the JVM heap at all. We do everything off heap for throughput purposes, among other things. And so Java CPP also does a neat thing of automatically generating Java native interface code. We never have to write JNI bindings. We just generate it. So we actually have a Java to C++ transpiler that then generates the JNI headers. And so this all actually can happen as part of an MVN clean package. It will actually automatically generate the native code necessary. So this is also how we package things like OpenCV. So we actually have something called Java CV that allows you to run everything from OpenCV in Java. And we automatically generate the JNI bindings for that. And so what you get is hardware acceleration on Maven Central, which, again, is kind of a novel concept. Like, a lot of people haven't thought about how to do this. So this is for data scientists. If anybody's like ever played around with Keras, it's what a lot of folks on Kaggle use for running deep learning applications. We actually import models from the Python folks. And so what that allows us to do is that allows you guys to just use our importer, and then you can just continue to consume models, not necessarily train them, or even have to escape to Python. For data developers, you define your pipeline via DataVec. You might import your model, or you might define it in Java, like your model, and then you deploy with Spring Boot, log on, play, whatever microservice thing you want to use. And then you can run training and inference on the GPU. And then this flexibility then allows for new scenarios, like I mentioned earlier, with Kafka streaming to something like TensorRT, which is specialized inference code for running compute on GPUs, where you're going to see a 3 to 5 times speed up running things in production. So a great use case of this is NASA. So the NASA Jet Propulsion Laboratory is actually a big user of DL4J. They converted from Google's library TensorFlow to us because they had a Java-based pipeline to deploy. Turns out that's what most of you guys do. So the Apache Tika project has actually adopted deep learning 4J for parsing images. And so why did they do that? That's because they had a whole lab of students using Python with an Apache Tika-based pipeline. They spent 3 months trying to do Java to Python to Java. And that failed miserably. So the second we had snapshots out for just doing transfer learning, they switched over to us immediately because we had the ecosystem and the JVM integrations, the integrations with the rest of the ecosystem. Not just some bindings, but actual integrations. So this is something I think you guys think about more than data scientists do. But if you're a developer, that's who we're for. That's why I'm at this conference. So with that, I will actually take questions. Thank you. Come on, guys. Crickets? Really? Come on. All right. All right. If you guys, okay. So, all right. Oh, right. Okay. I might have forgotten about that. So the question was explaining how you do low latency with the GPU. So this latency hiding thing I mentioned was you have some data you want to load in the GPU. So in another thread, we load data in the background. And what we do is when we allocate an ND array, it actually allocates memory on the CPU and the GPU. And then it loads data into the GPU automatically. And so when you're loading data from disk and you create an ND array or a matrix, it will automatically allocate memory on the GPU. So as long as you do that in another thread or in the background, you can basically benefit from having everything pre-allocated when you're going to need that array, when you're going to need that piece of memory. So that's what you're doing is you're achieving compute with loading the data at the same time. A lot of GPUs actually have multiple lanes, multiple PCIe buses for loading data into it. So what you're going to do is you're going to use something called a CUDA stream, which will say stream this data to the GPU in the background while running compute on this thread. All right. Okay. We all good? Okay. So we import, so the question was, what pre-trained models do we have? We mainly have examples, and we're actually going to be importing a lot of the pre-trained models from the Python ecosystem, like Keras and Caffe, that already have those libraries. That's what our model import is for, is to be able to support those. So if you have a pre-trained model on the internet somewhere that you want to run, we can probably support it via model import. That being said, we're also building our own model zoo as well. Oh, indeed I did. All right. So I had the yeah, sorry, like I was ranting and went a little over. So I can so that I can show you real quick. So I'm just going to rerun this here. Okay, so this is actually our training UI in action. So what we're doing is we actually update the training in real time. And so you'll see this is MNIST. So this is actually the learning rate going down. This is actually the error going down. So this is the error of the neural net as it's learning from the data. So this is an example of the model architecture. This is what I was showing you guys. So you can actually click, and you can actually inspect like the individual parameters, and the actual updates for individual layers. Here's the system. So this actually also covers things like the JVM memory allocated memory off heap. So this is what I was telling you, is you can actually track all your system information via our UI. So when you're running training, you're gonna want to instrument it with something to monitor and see, is my neural net learning, and how much memory is it taking up? And so you can use the UI in real time as the neural net's kind of learning. So yeah, so here's the model later on. So you'll see the error converge. So this was gradient descent, like I mentioned. So you'll see the error it becomes static very quickly. Oh, so the y-axis is actually the error, and the x is the iteration number. So the error, so that's the objective function. So the neural network has an error, like these are the number I got right, and then this is kind of the error over time. So this is your loss over time, and then so loss and iteration number. Right. So it's relative. So the problem with trying to set an absolute magnitude for the error is it's relative to the batch size, like the number of data points you're looking at once. So and the loss function. So we usually we usually sample it and figure out what the bounds are, and then we dynamically update the bounds as necessary. This is all D3 based, so this is all going to be dynamic. Okay. All right. Okay, good to go. Yeah, this is all running on the so this is all running on the GPU. So one thing of note with ND4J is you just have to include something called an ND4J backend, and you say ND4J CUDA, and it automatically runs everything in the GPU. No code changes. It's basically hardware as a jar file. Okay. No, so the only thing you have to have installed is, if you're using the GPU, is CUDA, and then we do the rest. So you install CUDA as you normally would, and then you basically just run everything from Java. After that, you run everything in Java. So no compilation required, no compile from source. Okay. All right, thanks folks, it's been good.